The next topic in this unit is called speed and velocity. So first definition of speed, it's the rate of change of distance with respect to time. So it's how fast the distance the object is traveling is changing, basically. It is how fast an object moves, and the SI units are meters per second. So there can be kilometers per hour is another example of units for speed, and there's other combinations, but the main standard units you see most of the time in physics books are meters per second. If the distance increases at a constant rate, then the object is said to be moving at a constant speed. So in this table and graph, if you analyze it, you'll see that the distance is changing at a constant rate, meaning for an equal increase of distance, it takes the same amount of time. Okay? For every equal increase in distance, there is a consistent amount of time that increases. So that's what we call a constant speed. In this particular example, every 50 meters the object is going takes 10 seconds. And vice versa. Every 10 seconds that the object is moving, it travels 50 meters. If you were to graph all these points, as is done on this page, the graph of any object going at a constant speed will be a straight line if you graph distance against the time. Okay, so that's a really important feature to recognize, the constant speed. It's often difficult to travel at the same speed every single millisecond, every single instant. So sometimes you move a little faster, sometimes you move a little slower. Hard to stay at the exact constant speed. So we'll often calculate an average. And we can calculate an object's average speed by dividing the total distance the object travels by the elapsed time. The formula is given right here. Average velocity equals distance divided by elapsed time. Okay, so just a simple division. Based on this formula and based on this formula and the symbols used, notice you don't see any harpoons. There are no harpoons, so that makes speed a scalar quantity, meaning there is no direction involved in speed. We can talk of an object's instantaneous speed. That's theoretical, it's like a concept. It's supposed to refer to how fast an object is moving at a very specific instant in time. So it's not an average, it's at a very specific instant. How fast are you going? It's kind of hard to measure, actually. Actually, all measurements made of instantaneous speed are actually just approximations. But a car's speedometer, for example, as the image shows, is supposed to give a pretty accurate representation of how fast something is going. So this car at this very specific instant is going at about 55 miles per hour. Similarly, a radar gun that a police officer might have to measure is supposed to measure the instantaneous speed, how fast a car is going, to see if they're obeying the law and driving at the speed limit. Okay, so that was constant speed. Now we have a term called constant velocity. So speed and velocity end up being two different words in physics. In everyday life, people may use them interchangeably, but in physics, they have different definitions, and you have to use the right word for the right situation and for the right calculation. So the definition of velocity is here at the top. It's the rate of change of displacement with respect to time. And I underlined the word displacement. So speed, so going back to speed, speed was distance divided by time. And it was a scalar quantity. However, velocity now is different. Velocity's definition is displacement divided by time. So that's why lesson 1 was try to explain the difference between distance and displacement. because you need to know the difference between these two so that you can understand the difference between speed and velocity. Speed matches with distance. Speed matches with distance, but velocity matches with displacement. And you may recall that displacement is a vector quantity, so a direction is needed. If displacement changes at a constant rate, then the object is said to be moving at a constant velocity. But we also use the term uniform motion to represent constant velocity. So if you ever see the words uniform motion, it means constant velocity. Another way to describe uniform motion is motion in one direction at a constant speed. So if you are going in a straight line at a constant speed, then you're going at a constant velocity. However, if you're not going in a straight line, if you're driving in curves, for instance, even though you may be going at a constant speed, your velocity will not be constant, because by going in curves, your displacement is going to be changing direction all the time. All right, example 1, uniform motion or not, or in other words, constant velocity or not. Or in other words, is it going in a straight line at a constant speed or not? Okay, so A, running in the same direction at a consistent 5 meters per second. Yeah, that is going in a straight line because it says same direction. And the constant speed is consistent, so it is constant velocity. A curling stone slides down the ice and stops on the button. This would not be a constant velocity. It's not uniform motion because the wording of the question says it stops. So it must be slowing down. So it is not going at a constant velocity. An apple falling from a tree. It is also a no. This one may be a bit more difficult to realize, but you have to understand that the apple is actually speeding up. As an object falls down, gravity pulls it down, it'll make it speed up. The apple actually started at rest, if you think about it. It was started at 0 meters per second when it was attached to the tree, but when it falls down, it must be picking up speed. And then D, a satellite orbiting the Earth at a constant speed. This one will actually be a no. Even though it's going at a constant speed, that's not the same as constant velocity, because a satellite orbiting the Earth is curving. It's going in a circle approximately, so it's changing direction all the time. So we would actually say no, it is not going at uniform motion. So similarly to speed, velocity is very rarely constant because it's just really hard to go at the exact same number the whole time. So again, we can calculate an average instead, and the average will be calculated by taking the total displacement an object travels and dividing it by the total elapsed time. Notice there are harpoons, meaning average velocity is a vector quantity. And then instantaneous velocity is theoretically a measure of how fast and what direction something is going at a very specific instant in time. It's very difficult to determine that. Usually it's just an approximation, but it's supposed to be how fast and what direction an object is moving at an instant in time. So something pretty conceptually important to understand is that instantaneous velocity and instantaneous speed will have the same magnitude. They're both measuring how fast something is going at a specific instant. So they're going to be the same number. The only difference is that the velocity will have a direction, but the speed will not. On the other hand, average velocity and average speed most of the time do not have the same magnitude. Okay, there's a big difference between instantaneous and average. Uh, if if I travel in curves, again, if I travel in curves, my average speed is distance divided by time, but my average velocity, so it's got a harpoon now, is displacement divided by time. And when you calculate these two, you will end up with different numbers. That's because the distance is the entire length of the path traveled. Okay, so it's the whole curve, how long it is a distance. But the displacement is much shorter. The displacement is only the blue line I drew there. And it's a lot shorter than that curved line. So distance and displacement have different numbers, and therefore average speed and average velocity will be different numbers when you calculate it. Okay, so we will do some examples. A person moves 75.0 meters to the right in 20.0 seconds, followed by 25.0 meters left in 5.0 seconds. Determine the average speed, determine the average velocity. So I'm going to draw a little picture here. So this can be the start, and they go 75.0 meters right, and then we'll turn around and go 25 meters left. Okay, so we have 75 meters right, and then 25 meters left. Okay, and furthermore, the 75 meters took 20 seconds, and then the 25 meters took 5.0 seconds. All right, A, determine average speed. So the symbol for average speed is V with the subscript AV. In the formula, do you remember it? It is distance divided by elapsed time. And the distance is going to be the total length. Okay, remember this? I'm going to just write that down. Total length of the path is the distance divided by the elapsed time. So the total length of the path traveled would be 75 plus 25 meters. That's the total length of the path. And the total elapsed time would be 20.0 seconds plus 5.0 seconds. Actually, the meters up top should have point zeros on them as well. Okay, so I'll add, the numerator would be 100.0 meters. The denominator would be 25.0 seconds. And when you divide 100 by 25, you get 4. However, with significant digits, there should be 3 significant digits due to the denominator here. So the answer of 4 only has 1 significant digit, but I need 3 significant digits. So I actually need to put 0.00 and then the units. Okay, this is the correct final answer. If you just left it at 4, you would lose half a mark. Okay, now B, the average velocity. So the average velocity is V subscript AV with a harpoon. It's a vector. And the formula is displacement divided by elapsed time. Now, displacement, if you recall from lesson 1, it's the straight line from start to finish. I'm going to draw that in blue here. The straight line from start to finish. And that line is going to be 50 meters, just looking at the geometry of the situation. So it'll be 50 meters to the right because direction is required for displacement. And the time, sorry, it should be 50.0. I'm not showing you proper habits here. The number of digits matters. 75.0, 25.0, and then 50.0. So it'll be 50.0 meters. And then the time is, again, 25.0 seconds. Okay, so we'll divide these out. You get 2, but to 3 significant digits, it'll have to be 2.00 meters per second to the right. All right, so there's the first example of average speed versus average velocity. As I said in the previous slide, the numbers are different. Speed and velocity are not the same thing. One of them is 4, the other one is 2 for this question. They are different things. Example 3, Caitlin runs 4 laps around lane 1 of a standard outdoor track. She runs the first 3 laps at a constant speed of 3.2 meters per second. Her final lap takes 160 seconds because she is tired. A, determine her average speed. B, determine her average velocity. So I am going to do part B first because part B is really quick. Average velocity is displacement divided by time. And the displacement is 0. She stopped where she started. Okay, the straight line connecting her starting point to her stopping point is not even a line at all. It's 0. So 0 meters per second would be the answer for part B. All right, A. So the average speed is going to be the distance divided by the total time. So the distance she runs is 4 times 400 meters. If you remember, one length around lane 1 of the track is 400 meters divided by the total time. Now the total time is, like, we need to figure that out actually. So I'm going to do that off to the side here. So for the first 3 laps, she ran, so that would be 1,200 meters. And she did that at 3.2 meters per second. So how many seconds is that overall? You can get the answer to that by dividing. And 1,200 meters divided by 3.2 meters per second. That'll tell you how many seconds it took to run those 3 laps. And then the final lap was straight up 160 seconds. They told that to us straight up. So the total time then, going back to my solution here, I'm just going to write the expression. Example 4, how much time does it take for an object traveling at 40 kilometers per hour to travel 750 meters? Okay, first of all, 750 meters, that's not even 1 kilometer. Okay, that's less than 1 kilometer, which is 1,000 meters. And 40 kilometers per hour is the speed limit actually on residential roads here. So think of a car driving down your street. How long is it going to take before it drives 750 meters? Okay, so it's not going to take too long. Maybe like a couple minutes, maybe not even a couple minutes. Okay, so this is like sort of an estimation of what the answer should be close to. To do this calculation, if you write the formula, speed is distance over time, and you try to solve for the time, you have to do some algebra to do that. And this algebra involves multiplying both sides by time first. When I multiply both sides by time, I get velocity times time equals distance, okay? Because distance divided by time, multiplied by time, just equals the distance. After doing that, I will divide both sides by average velocity. If I divide the left side by average velocity, it just cancels out. I'm left with delta t. And divide the right side by average velocity. It'll be d divided by average velocity. So that's how you do the algebra to isolate the equation. And now you're going to be able to solve for the time, which is what the question asks for. How much time does it take? However, we're not ready to plug in the two numbers given in the question because the units are not consistent right now. One's in kilometers per hour, the other's in meters. You have to have consistent units before you can use the formula. So my two choices are convert kilometers per hour to meters per second, or I can convert the 750 meters to kilometers. Now, because I know that my answer is going to be not that much amount of time, I'm probably going to lean towards converting this into meters and seconds. Okay, if it was a different situation and I thought the time would be a number of hours, then I probably would have done the other way around. But because I think that the amount of time is not going to be more than a couple minutes, I am going to convert the kilometers per hour into meters per second. So how do you do that? So convert to meters per second. So how do you convert kilometers per hour to meters per second? There is a conversion factor, which I'm going to call a shortcut. And the conversion factor between kilometer per hour and meter per second is 3.6. For just like how there's 12 inches in a foot, so there's like 12 is the conversion factor for feet and inches. There's 2.2 pounds in a kilogram, so 2.2 is the conversion factor between pounds and kilograms. The conversion factor between kilometers per hour and meters per second is 3.6. But now, do I multiply by 3.6 or do I divide by 3.6? It turns out that we will divide when we're doing this conversion. And if we had meters per second and wanted to convert to kilometers per hour, we would multiply by 3.6. Now, where does this number 3.6 come from? Well, it comes from the fact that 1 kilometer is equal to 1,000 meters, and that 1 hour has 3,600 seconds in it. So a kilometer per hour is the same as 1,000 meters per 3,600 seconds. And that just reduces to 1 over 3.6. So therefore, if I want to go from kilometers per hour to meters per second, I actually just divide by 3.6. Okay, so I can go back to solve my problem now. My time will equal the distance 750 meters divided by my speed, which is going to be 40 over 3.6 meters per second. Okay, 40 over 3.6 meters per second. So I'll pop that into a calculator. And that gives me 67.5. This does need to be rounded to 2 sig figs because of the 40. Not because of the 3.6, because 3.6 is an exact number. We actually would ignore that from our significant figures calculation. But because of that 40 there, our answer needs to have 2 significant figures. So this answer will be rounded to 68 seconds. So it was just more than a minute. My initial estimation was not too bad. I said less than a couple of minutes. All right, last example here. Mr. Korsmit begins 20 meters north of Mr. Tang. If Mr. Korsmit runs at a constant 3 meters per second north, and Mr. Tang runs at a constant 4.5 meters per second north, When will Mr. Tang catch him? Okay. So a classic problem in physics involves two objects. One of them is chasing the other. When are they going to meet each other? So I'll draw a picture of the situation here. So Mr. Tang, that can be right here. And then I'll have Mr. Korsmit start 20 meters ahead of me. Okay, so that's 20 meters. And Mr. Korsmit is going to be moving at 3 meters per second, 3.0 meters per second. Mr. Tang is going to be moving faster, obviously, at 4.5 meters per second. Okay, so I'm going to eventually catch him because I'm running faster than him. And there's a couple of ways to approach this. I think the most straightforward way to approach this is by calculating the rate that the distance between us is shrinking. How fast am I making up ground? Basically, how much faster am I running than he is? So that'll be 1.5 meters per second. So Mr. Tang is running 1.5 meters per second faster than Mr. Korsmit. So the distance between them is shrinking by this much. Shrinking by this rate. Rate is a much better word to use. Okay, so we're 20 meters apart, and this 20 meters is shrinking by 1.5 meters per second. So how much time will it take for me to close that gap fully? That can be now calculated with the speed is distance over time formula. Using a speed of 1.5 and a distance of 20, I can find how much time that will elapse. So this algebra, if you rearrange things, you end up with 20 divided by 1.5. Okay, that's just algebra skills. And then I'll put that in the calculator. And round it to 2 significant digits, the answer is 13. Okay, so that's your very first example of one object or two objects meeting, and when do they meet. You'll have more as the course goes on. They're going to get a bit more complicated. This one, we were both going at a constant velocity. But later, we're not going to be going at a constant velocity, or maybe one person starts running, and then it's a few seconds before the other person starts running, and there's complications like that that will force you to think a little bit harder. But this was your kind of your introductory example.